Okay, welcome to the Southwest England field trip and the field guide that goes with it, which you should all have. I'm going to first introduce the people who are going to be doing the presenting. I'm Mike Searle and Professor Laurence Robb from Oxford University. George Willment was a fourth year student who was working on the lizard complex for his fourth year project. So Southwest England forms the northern part of the Paleozoic Veruscan orogenic belt. And this is a mountain belt that extends all the way from Central America to Eastern Europe, and it clips the southern part of the British Isles around the Lizard Peninsula in particular and the Southwest England geology. So you can see from the map that the Veruscan orogenic belt follows a lot of the same trend of the earlier Caledonide orogeny. Now, we've seen the Caledonide orogeny from the field trip to northwest Scotland last year, and the Caledonide belt extends from eastern Greenland, western Norway, all the way down through Scotland, through Ireland, to Newfoundland and the Appalachians. And the Veruscan orogenic belt, which is a later orogenic belt related to the opening of the Rheic Ocean, extends right the way across Central Europe, from southwest England across into France, Germany, the Czech Republic, and even further east towards the Carpathians. So the Rheic Ocean opened in the early Ordovician, and it attained its greatest width during the Silurian, and then it closed during the Devonian Carboniferous. Now, the earliest parts of this orogeny are best exposed in the lizard complex, which is an ophiolite sequence comprising oceanic crust and upper mantle, emplaced onto the passive margin of Avalonia, the England plate. And the lizard ophiolite in Cornwall is the biggest and best exposed ophiolite in the entire Veruscan orogeny, which is why Southwest England geology is so important. Okay, I'm standing here at the village of Coverack on the east coast of the Lizard Peninsula, and we're going to look here at the complex of rocks called the lizard ophiolite sequence. Ophiolites are extremely important rocks because they are manifestations of what the oceanic crust and upper mantle looked like prior to the collision of the continental plates. So in the lizard we have a full section of the ophiolite sequence, which I'm going to run through from bottom to top. And this is the most complete ophiolite section anywhere in the Veruscan orogeny, so it's extremely important regarding the tectonics of the early phases of the Veruscan orogeny. So an ophiolite is defined as a series of crustal and mantle rocks derived from the oceans, which are emplaced onto continental margins. So in the lizard we have a beautiful section of ultramafic rocks. These are peridotites, which is a general term for including rocks composed of olivines and pyroxenes. So the standard rock we see in the lizard complex here is either a hartsbergite, which is olivine plus orthopyroxene, or a lertzolite, olivine, orthopyroxene, clinopyroxene. These rocks have all been heavily altered, so what we see now are serpentinites. And serpentinite is just an altered peridotite. So olivines go to serpentine minerals, and the pyroxenes go to a mineral called bastite. These rocks here are what we call residual mantle because they have had melt extracted from the mantle to create the crustal sequence. And the crustal sequence is composed of plagioclase-bearing rocks. There is no plagioclase in the mantle, but the crust is composed of plagioclase-bearing gabbros. And the most spectacular examples of the difference between the oceanic crust and the upper mantle is in a sample like this. So the boundary between the mantle and the crust is a geophysical boundary that we call the Mohorovičić discontinuity, or the MOHO for short. And the MOHO divides the ultramafic mantle, olivines pyroxenes, from the mafic crust. The mafic crust has plagioclase in it, as well as olivine pyroxene hornblende. Now, this sample here actually came from the Oman ophiolite, which is the biggest and best ophiolite complex in the world. And it is a spectacular boundary between the mantle, peridotite, and the mafic gabbro. Not everywhere in ophiolite sequences is the MOHO a straight line. In fact, it's very rarely a straight line. In this sequence in the lizard, it's a zone approximately 500 meters and maybe up to 1 kilometer thick of interbanded peridotites and gabbros with a whole variety of different ultramafic and mafic rock types that we will be seeing shortly. So the ultramafic mantle is separated from the mafic lower crust by a zone that we call the Moho transition zone, and that is exposed along the beach here at Coverack. So we will see all of these rocks in the next parts of the video. As you go up the crustal sequence of the ophiolites, the gabbros represent the magma chamber underneath an oceanic spreading ridge. So if you look underneath the mid-ocean ridge of the Mid-Atlantic, for example, there will be a gabbroic magma chamber composed of rocks like these, which are feeding tholeiitic magma upwards through a series of sheeted dikes. Now, sheeted dikes are finer grain size than the gabbro, so you're going from gabbro to dolerite to basalt as you go up the ophiolite sequence. The sheeted dikes are extensional features. Mid-ocean ridges are extensional structures. Magma is fed up from the gabbroic magma chamber up a series of these sheeted dike complexes, and the sheeted dikes feed the pillow lavas at the top. Now here in the Lizard, we don't see the pillow lavas. They've been eroded off the top, and the sheeted dikes are about 5 kilometers up the coast here at Coverack. So we're going to start off with looking at structures in the upper mantle, and these are particularly partial melt structures of how you extract basaltic melt from an ultramafic rock, and you're left with something like a Harzbergite or a dunite residue. Dunite is pure olivine. In terms of mineralogy, the world's chromite, nickel, vanadium deposits are all found in ultramafic rocks, either in intrusive complexes or in ophiolites. The uppermost parts of ophiolite complexes are typified by copper deposits. One more thing to mention on ophiolites is there's a big debate whether the origin of ophiolites happens at a mid-Atlantic type ridge, a mid-ocean ridge, producing mid-ocean ridge basalt, morb, or whether they're formed above an active subduction zone, in which case they're called supra-subduction ophiolites. Now, the evidence for the abduction of ophiolites comes in the form of the metamorphic Searle, which are the rocks structurally beneath the ophiolite. So the base of the ophiolite is a major thrust, the Lizard thrust, that emplaces the ultramafic-mafic complex of the oceanic crust and mantle over at first oceanic rocks and eventually continental margin rocks as the ophiolite is emplacing from the Rheic Ocean onto the passive continental margin of Avalonia. So these thrust sheets here we will be seeing later on in the video. This is classically called the metamorphic Searle. And the metamorphic Searle of the ophiolite is a thin sequence of inverted metamorphic rocks going from granulites to amphibolites to green schists. And they are upside down, which means that the heat for the metamorphism is derived either from the ophiolite mantle or more likely from the deep mantle wedge during emplacement. And as the thrusts are emplacing from deep oceanic to shallow continent, you're going progressively from amphibolites to epidoamphibolites to green schists. And underneath the metamorphic Searle is a whole series of sedimentary rocks, turbidites of the Gramscatho group, which are involved in thrust sheets emplacing onto the continental margin with spectacular folds and thrusts that we will see towards the end of the video. Okay, this is the southern end of the beach at Coverack, the headland, and we're now down just below the Moho into the top of the mantle sequence of the Lizard ophiolite. Now the mantle is all made of peridotites, olivines and pyroxenes, so they're dark-looking, black-looking rocks, no plagioclase in the mantle, and that's why they're so dark and black. So the original lithology that comprised the mantle was a spinel lertzolite. So it was a rock composed of spinel, olivine, orthopyroxene, clinopyroxene. As the melt rises adiabatically underneath mid-ocean ridges, it decompresses and you start producing mantle melt. And as that process goes on, you're converting a lertzolite to a Harzbergite and eventually to a dunite. So you're getting rid of first the clinopyroxene and second the orthopyroxene, and a dunite is the restitic mantle that's left over once you've extracted the tholeiitic basaltic melt to make the gabbros in the lower crust. So this rock here has very nice examples of orthopyroxenes which have been serpentinized to bastite, and olivines which have been partially serpentinized to produce serpentine. Serpentine minerals are the low temperature alteration products of olivine. This mantle rock is composed of orthopyroxene and olivine, so it's dominantly called a Harzburgite, and it's cut through by these pyroxenite veins. And these also contain big bastite pseudomorphs here, and also green olivine and a little bit of clinopyroxene, the olive green mineral. So these are olivine and pyroxenite veins intruding a restitic mantle. This rock here is composed of pyroxenes and olivines, and if you look at these big chunky crystals here, these are classic enstatites, which are orthopyroxenes, and they are orthogonal and they have a very prominent cleavage, and this is the easiest way to recognize them. They alter to bastites, which is a serpentinite type mineral, low temperature serpentinite alteration, but they're very prominent. They're large, shiny. All the shiny crystals here that you see are bastites after orthopyroxene. The other mineral is this olive green mineral here, which is typical of what the mantle is made of, and those are olivines. Olivine has a magnesium end member and an iron end member. These are mostly forsterite olivines. Forsterite is the magnesium end member, and they have this classic bottle green colour, very dark bottle green colour. The third mineral here is very minor in composition, probably 5%, but it's these crystalline, again green minerals, and these are clinopyroxenes like diopside. So this rock is composed of olivine, orthopyroxene, clinopyroxene, and a little bit of spinel. So this is a spinel lertzolite, and this is the deepest part of the mantle sequence that we see on the lizard Ophiolite.
Serpentinized peridotite. This thin section shows a plain polarized light view of one of the serpentinized peridotites from the Coverack Bay sequence. In the peridotites, we have some fresh olivine, which has been preserved and has not been broken down. The majority has been, and it has been replaced by a yellowish, brownish serpentine mineral. There are some relic grains of orthopyroxene in the rock as well. You can distinguish these from olivine by their well-developed cleavages and their lower birefringence.
When you hydrate a peridotite, you end up with a serpentinite, and this is what the lizard Ophiolite is famous for. It's serpentinite rocks. Serpentinization is purely hydrated olivine, and it has the form of several different textures, including this one, which is a classic texture of serpentinite veining. These veins here are formed of various serpentine minerals, lizardite, which is named after this Ophiolite, chrysotile or antigerite. But they're all low temperature alteration products as a result of hydration of olivine. These serpentinite veins is where you get asbestos as well, and also talc. So the classic alteration of an original olivine bearing peridotite is talc, serpentine, asbestos, and that is where these veins are occurring in hydraulic fractures as the water is escaping. So these rocks are serpentinized, but this is 100% altered to serpentinite.
We're sitting here on a rock that is, as you can see, really quite different from the spinel lertzolite that we've just come from. And the main difference that we can see here is that the rock is paler in colour, and it's characterized by the spotted sort of white colour, and the mineralogy here is really quite different. This rock is a gabbro. It's characterized by two pyroxenes, orthopyroxene, the darker dark green minerals that we see on this face, clinopyroxene, the lighter, more apple green colored mineral, and then of course plagioclase, the white interstitial mineral that you find all over here. So this rock is essentially made up of clinopyroxene, orthopyroxene, and plagioclase. The main difference is that it has a higher alumina content. So essentially we're looking at a fractionated series here, which started off in the lertzolitic rocks that we saw at the previous outcrop, dominated by olivine, orthopyroxene and clinopyroxene. And as we fractionate the system, the alumina content has increased to the extent that we're now able to crystallize significant proportions of feldspar. And it's of course the feldspar that is the predominant mineral in this particular gabbro. This we call a cumulate gabbro because we're sitting in the middle of a magma chamber, and the feldspars and the pyroxenes have accumulated from the magma, settled down onto the floor of the magma chamber to form this cumulate textured gabbro. Where are we in terms of the ophiolite complex as a whole? Essentially, if we look at the cross section, we're sitting just here above, directly above the Moho transition zone. We're sitting in the zone of cumulate gabbro. And again, as I say, this is characterized by the first appearance in the lower crust here of significant amounts of feldspar. As you migrate upwards, the rock becomes more and more differentiated. It would presumably become more alumina rich and more feldspar rich as you move upwards. But right here at the base of the crust and just above the Moho transition zone, these cumulate textured gabbros are very typical.
Gabbro. This is a thin section in crossed polar views of a gabbro from Coverack Bay. This is essentially a bimineralic rock. There's coarse clinopyroxene of the chemical variety diopside, and there's calcic plagioclase as well, in which you can see quite nice lamellar twins. They're fairly well formed. This rock has an unfoliated texture. It has a magmatic texture. There's no metamorphism or recrystallization at all.
As we walk from south to north across Coverack Beach, we're walking across from the upper mantle to the lower crust. This is what we call the Moho transition zone. So we're crossing the sequence here from the upper mantle peridotites into the lower crust gabbros. And the gabbros are interpreted either as a magma chamber below the volcanic edifice, below which the cumulate sequences are dropping out. So here we have cumulate interbanded gabbros and peridotites. And as we go up the sequence, we lose olivine, we lose orthopyroxene, and hornblende starts to replace clinopyroxene. So these gabbros are very high temperature. They're crystallizing at temperatures about 900 degrees centigrade. So within this massive gabbro sequence here, we have some spectacular examples of ductile myelinized gabbros. And these are related to extensional faults, low angle normal faults that are dipping towards the axis of the spreading center, along which the crust is extending. So what happens in the lower crust below a mid-ocean ridge is that you have these ductile extensional myelinites. And this sample here is taken from the Carrick-Lewes myelinites just up the coast. And they started life off as gabbros, but they've been deformed by this incredibly high temperature fabric. The temperatures of deformation here are probably above 600, 700 degrees centigrade. Temperatures at the base of the crust during extension. So the uppermost parts of the lizard ophiolite complex extend north of the coast here at Coverack, and we're not going to have time to film them today. But what we're missing is the uppermost part of the gabbros becomes finer and finer grained, and eventually you can see the gabbros accumulating magma to feed up into the pillow lavas along the sheeted dike complex. The sheeted dike complex is exposed right at the top of the ophiolite sequence in the lizard. And in that upper crustal section, we have these very unusual rocks called plagiogranites. These rocks are composed almost entirely of plagioclase, with maybe 5% hornblende, possibly 1 or 2% quartz. But they are the most fractionated phase of the entire sequence. And they're very important because these most felsic parts of the ophiolite are the only parts that have magmatic zircon. And we can use the zircon for dating the age of the crystallization of the plagiogranite, the age of crust formation, by using uranium-lead isotopes on zircon. And these ages on these plagiogranites from the lizard have come out at about 397 million years, Devonian, Middle Devonian age. And all of this age range of the various ophiolitic rocks corresponds to the age of formation of the oceanic crust. After the age of formation of the oceanic crust, the abduction process started, which was the process in placing the entire Ophiolite thrust sequence onto the passive continental margin of the Avalonia plate to the north.
We're sitting here on a unit called the Trebot Hornblende Schist, which is a rock which is probably gabbroic as a general term, made up essentially of equal proportions of plagioclase and hornblende, as you can see in this rock type here. Quite a lot of plagioclase in some of these units. Some of these rocks might even be almost tonalitic in composition, but generally we refer to this again as a gabbro. But the interesting thing about this particular unit is that you'll see it's really quite strongly foliated, and yet it's cut by really coarse pegmatoidal veins, pegmatites, which are also made up of plagioclase and hornblende. So we've got a pegmatitic phase, which is almost exactly the same composition mineralogically as the host rock itself. So we've got a kind of a gabbroic hornblende plagioclase rock cut by pegmatites made up also of hornblende and plagioclase. Again, as I said, the interesting thing though is that the host rock is deformed, whereas the pegmatites themselves are not deformed. They essentially cut right across the foliation in the host rock itself. And yet, this must all be part of the lizard Ophiolite complex. So these rocks would have been emplaced one after the other, but over a very short space of time, and yet the deformation took place before the intrusion of the pegmatite. The only conclusion that we can come to then is that the sequence of events, intrusion and emplacement of the ophiolite, crystallization of the ophiolite, emplacement of the pegmatite, and a deformation all took place over a relatively short period of time, almost instantaneously geologically.
To wrap up the Ophiolite sequence that we've seen on the lizard, here we've got a sketch diagram of the oceanic crust, what it should look like if you drilled a hole through the oceanic crust down to about 10 kilometres. In green here we've got the mantle upwelling beneath a mid-ocean ridge. The mid-ocean ridge is a line of volcanoes similar to what you see along the Mid-Atlantic Ridge or the East Pacific Rise. And these volcanic rocks are fed from a gabbroic magma chamber. So these rocks here in the mantle are the periddotites, lertzolites, harzbergites, depleted mantle from which the basaltic melt has been extracted and moved up to the lower crust. So this is ultramafic and this is mafic. The incoming plagioclase comes in here at the cumulate sequence. The cumulate sequence is either the base of the magma chamber or the base of these gabbroic sills where the heavy minerals settle out, the olivines and the pyroxenes, with the plagioclase forming a intercumulus texture. The magma is fed up from the gabbroic lower crust up through the sheeted dikes to feed the pillow lavas. So you have a fining grain sequence from gabbro to dolerite to basalt as you go up the section. And the final section at the top, you can have radiolarian cherts, deep sea sediments interbanded with the basalts. And that's how you date ophiolites, from fossils, either radiolaria that are interbanded within the basalts, or from the latest fractionate phases, which are the trondhjemites or the plagiogranites, which are extracted generally from the top of the gabbro sequence into the sheeted dikes. So extension at the mid-ocean ridge, fed eventually by decompression melting along the axis of the ocean ridge, major fault systems bounding the central graben system of the spreading centre, and this is what the full Penrose Ophiolite sequence should look like. So we've seen everything in the lizard from the mantle up here to the sheeted dikes. The pillow lavas have been eroded away and we don't actually see them on the lizard.
Another very interesting feature of the environment, the ocean floor environment here, is the way in which the mineral deposits form. So remember, this oceanic crust is covered by substantial depths of seawater, and we also have these very prominent listric normal faults which extend down into ductile shear zones at greater depth. It's not difficult to imagine that seawater is actually being drawn down into these faults. Cold seawater initially, but as soon as you get down to this hot environment here, the seawater heats up very rapidly and can attain temperatures of up to 300 degrees centigrade. So very rapidly the seawater gets heated up, and in so doing it actually starts to dissolve and extract the metals which are already concentrated in the mid-ocean ridge basalt, particularly copper. So copper actually is partitioned into the aqueous fluid, concentrated quite significantly, and as these fluids come back up the mid-ocean ridge to form what we call the black smoke events, essentially what happens is the copper concentrated in the fluid gets precipitated on the ocean floor to make what we call a volcanogenic massive sulfide deposit. And places like Cyprus, for example, there are many examples of very rich copper deposits associated with this ophiolitic environment, where copper is concentrated in the fluid but then precipitated around the black smoke events to form these massive sulfide copper deposits.
Now that we've seen the complete ophiolite section on the lizard, including the upper mantle peridotites and the mafic crustal section, the next problem is how do you get a slice of oceanic crust and upper mantle onto the leading continental margin of Avalonia. The evidence for that all lies in the metamorphic Searle, which is the next set of rocks that we're going to look at here on the lizard. We are at Church Cove on the east coast of the lizard, and we're looking north and east along the base of the lizard ophiolite thrust. So Koverack is 2 bays in and Kennock Sands is just beyond that. So we are looking northeast at all of the high parts of the cliff here are serpentinized ultramafic rocks belonging to the base of the lizard ophiolite, and the rocks down there near the coast are the amphibolite metamorphic Searle. The pink rocks you can see in the distance along the first cove there are the Kennock gneiss, and those are the same as we saw at Kennock Sands. These felsic gneisses intruding up into the base of the ophiolite thrust sheet. So the contact is very sharp and brittle. Here it's a thrust fault, a late thrust fault, and that same fault can be traced all the way along the east coast of the lizard. So this is a very thin sheet of abducted ophiolites. Unlike the intrusive contacts at Kennock Sands, where we saw the Kennock gneiss intruding up into the peridotite, here we have a very sharp contact. This is a brittle thrust fault, the lizard thrust, that in places serpentinized peridotites, Hartsbergites, over Kennock gneiss. All of these rocks are very brittly deformed and late fractures cut right through the footwall. So George has got his hand actually on the contact. Above him is the peridotite and below him is the Kennock gneiss. And here it is thrust contact, not intrusive. We are north of the village of Cadgwith on the east coast of the lizard, and we're looking at the structures along the base of the lizard ophiolite complex. And in this little quarry, we see a very distinct sequence of rocks. Below and above a major thrust fault. This plane here divides 2 very different rock types. Above that plane we have typical Hartsbergites, depleted mantle parts of the ophiolite, and these are made of bastite pseudomorphs after enstatite and olivine. So the Hartsbergite is the depleted mantle part of the peridotite of the lizard ophiolite. And along the base of the ophiolite we have a very sharp contact. This is a thrust fault which emplaces the lizard ophiolite over these rocks here. And these rocks are very different. These rocks are very dark, they're very banded, highly deformed. These are amphibolites. These are composed of hornblende and plagioclase with a bit of secondary epidote. And this is the top of the metamorphic Searle. The metamorphic sole was formed as a result of heat coming out of the mantle during emplacement of the ophiolite towards the continent. So whereas the periddotites of the lizard were formed at about 1100, 1200 degrees centigrade in the oceanic environment, these rocks are metabasalts, so they were originally basalt, subducted beneath the ophiolite, and these form at temperatures of anywhere between 750 and 800 degrees centigrade, and pressures anywhere between 5 and 8 kilobars. So the pressures in these rocks are much greater depth than the thickness of the ophiolite, and therefore the metamorphic sole is a record of the subduction process that initiated the abduction of the ophiolite. This outcrop here is at the top of the metamorphic sole, so we are immediately underneath the lizard thrust. Above us is the ophiolite, the mantle sequence of the ophiolite, olivine, enstatite, hartsbergite. And we see here two different rock types. The amphibolites are these dark black rocks, and these are composed of hornblende, plagioclase, and a little bit of epidote. In some metamorphic soles you can also find clinopyroxene, but in this outcrop we don't see any. Where you have clinopyroxene, hornblende, plagioclase, the highest temperature part of the metamorphic sole is a granulite facies rock. These are actually upper amphibolite facies rocks, and these are formed at temperatures around 750, 800 degrees centigrade and pressures anywhere between 5 and 8 kilobars. So the pressures indicate depths of formation much greater than the ophiolite thickness, and the heat to form these rocks has to come out of the mantle, because we're now looking at an oceanic subduction zone in which old metabasaltic rocks were subducted down beneath the oceanic plate with the ophiolite above. And that is the beginning of the abduction process. So this other rock type here, this pink one, is completely different. This is a granitic rock. It's composed of quartz, potassium feldspar, and plagioclase. And this rock has nothing to do with the ophiolite. It's completely different. This is a granitic rock formed from crustal melting of sediments beneath the abducting ophiolite during the late stage, and it's been injected into the amphibolite of the metamorphic sole. This is part of a series of rocks we call the Kennet gneiss, and we'll see those in much greater detail in the next outcrop further down the coast. So here we're looking at the high temperature metamorphic sole of the ophiolite, and the pressures, the depths and the temperatures in these rocks recorded we can use to interpret the abduction process.
Amphibolite. Here is a plain polarized light thin section of an amphibolite from Landewednack. There's two main minerals. There's a calcic amphibole, which is probably the variety hornblende, and there's a calcic plagioclase. The plagioclase, unfortunately, is very intensely sorceratized and has this pinkish colour in plain polars. Normally it would look colourless if it was fresh. This is a result of retrogression of the rock as it was cooling down from peak metamorphism. There's also some minor opaque phases, ilmenites, rutiles, and maybe some biotite as well.
On this simplified map of the Lizard Peninsula, we're looking at the periddotites here in this mauve colour, and the Landewednack amphibolites, the metamorphic sole, in this green colour. And we're now here at the south end of Kennet Sands, where these red rocks occur on the map, and these are called the Kennet gneisses, and they're an enigmatic series of mafic and felsic rocks that are occurring right along the base of the ophiolite and sometimes intruding up into the base of the ophiolite. So the rocks I'm sitting on here are the classic hartsbergites of the mantle sequence. You can see these big bastite pseudomorphs after enstatite, and the black is all olivine, which has been serpentinized. So olivine orthopyroxene is a hartsbergite. When you serpentinize a hartsbergite, you're left with this rock here, and these are serpentinite veins that intrude during a late stage, and you can see the Fibrous minerals here are probably either serpentine with asbestos and talc. They're very, very soft when you rub your hands on them. And these are the late stage, low temperature hydrothermal veins of serpentine that cut a serpentinized Harzbergite. So if we look further up here, we're looking at a series of dark rocks and pinkish coloured rocks. These are the Kennet gneisses, and there are two types of gneisses. One is a mafic gneiss. Basically it's a hornblende, epidote, actinolite schist with plagioclase in, and the other one is a felsic gneiss, which we'll look at in more detail at the next outcrop. You can see the felsic gneiss, these pink dikes are intruding up into the base of the ophiolite. So from the field relationships here, it's clear that at least the felsic gneiss is later than the ophiolite, because the ophiolite is abducted onto the continental margin, and the mafic gneiss, which is possibly equivalent to the metamorphic Searle, and the felsic gneiss is intruding up into the Harzbergite. So the felsic gneiss has to be younger than the ophiolite abduction.
We're standing here on an outcrop of the Kennet gneiss. And as you can see, this rock unit is made up of two very distinct rock types. The darker unit is an amphibolite, almost certainly originally a mid-ocean ridge basalt, made up mainly of amphibole and plagioclase, and the lighter coloured rock here is a granite made up of quartz, potassium feldspar and plagioclase. You can see quite clearly that the granite intrudes and rafts off bits and pieces of the amphibolite. So the one unit appears to be intruding into the other. And in fact, if you step back and have a look behind us, from the close-up to the distance, you can see the intrusive felsic dike intruding into the Harzbergite of the ophiolite.
Okay, we are now at an outcrop here on Mullion Cove on the west coast of the Lizard, and this is one of the best localities for looking at the metamorphic Searle and the base of the ophiolite, the Lizard thrust. On the map, the Lizard peridotites are in this mauve colour, and the Lander-Wednack amphibolites, the metamorphic Searle, are in the green. So we're looking at this thrust contact that puts peridotite of the ophiolite over metamorphic Searle. Now here, there's a very strong boundary. This line I'm standing on divides peridotite rocks to this side from amphibolite facies rocks on the footwall this side. And this is a very straight line. It's a brittle thrust, which is the final stage of emplacement of the ophiolite. So the rocks above me are Harzbergites, exactly the same as we've seen over at Koverack, but in this case the orthopyroxenes are all strung out along a very high temperature ductile fabric. Both the orthopyroxenes and the olivines are stretched during the thrusting of the ophiolite over onto the metamorphic Searle. This is very high temperature deformation. Harzbergites and lertzelites deform at temperatures above 1100, 1200 degrees Celsius, whereas the metamorphic conditions of the top of the Searle are upper amphibolite facies. So the rocks in here are basically just hornblende and plagioclase with a little bit of secondary epidote, and you can just see little bits of partial melting, in situ partial melting. Partial melting of hornblende happens at 900 degrees centigrade, very high temperatures. And this fabric in the metamorphic Searle is parallel to the fabric at the base of the ophiolite. So we know that these are both related to early ductile deformation as the ophiolite was detaching and moving when it was out in the Rheic Ocean way out to the south. So the pressure temperature conditions of the metamorphic Searle are higher, indicate that the depths of burial of the metamorphic rocks on the footwall are higher than the thickness of the ophiolite above, which means that the contact was almost certainly some sort of subduction zone, a thrust fault tapping the mantle, onto which basalts were subducted, metamorphosed to amphibolite facies, and then extruded back out again. So many metamorphic Searles actually have a little bit of clinopyroxene, This one doesn't. If it did, it would be in the granulite facies, clinopyroxene, hornblende, plagioclase. This one is in the upper amphibolite facies. And as you go structurally down the metamorphic sole, you're going into lower pressure, lower temperature rocks. So the metamorphism is inverted, which means the source of heat has to be from the mantle wedge above the metamorphic sole. In the case of the Landerwednak, we are going from the typical amphibolites that we see here, down structural section to epidote amphibolites, finally into green schists, and at the base of the metamorphic sole is another thrust. So you have a thrust-bounded wedge in placing the ophiolite, peridotite, over the metamorphic sole, and those rocks in turn are thrust over unmetamorphosed sediments that we'll see later on further down on the west coast of the Lizard Peninsula.
We are stood now at Lubar, and to our southeast are the rocks of the Lizard Ophiolite, underlain by the metamorphic sole, and then coming structurally down section to where we are here, we are in the Gram Scatho group. This is a series of sandstone, siltstone turbidites that once formed the sedimentary sequences on the southern margin of Avalonia, which are now outcropped in a series of thrust-bounded knapsacks. And these record deformation related to ophiolite abduction towards the northwest. And if we look at these two features here, we can see in map and cross-section form the structural features that are associated with this. So the lineation and facing of fold hinges and strikes and dips of cleavages and thrust faults. And here we can see what those features look like in cross-section. And the strain ellipses and stereonet show the kinematics of each of those, and all of these are related to the northwestward emplacement of the Lizard Ophiolite over the Avalonian continental margin. Here at this outcrop we see an excellent example of a tight recumbent fold in the Gram Scatho group turbidites. So important features to note on this, firstly, are the bedding that pick it out. So here we go from the light grey silt and sandstone which grades through to the black mudstones. The next important feature to look for are the axial planar cleavages, which run parallel with the axial plane of the fold right through here. Looking at both of these together allows us to determine the facing direction of the fold, and the facing of the fold is the direction of younging along the axial plane. So as we know that grading in these turbidite sets is heading up the outcrop here, we know that the facing direction for this fold is to the northwest. And the other feature of this fold is the fact that it's bounded to the top by a fault, and its recumbency and facing allow us to determine that this has experienced a strong sense of northwestward directed simple shear.
This is a beautiful outcrop showing the styles of deformation in the Gram Scatho group. So in this, for example, here, we've got a recumbent fold sitting above a thrust plane. And this is a classic hanging wall anticline with thrust below and above. If we come further down here, this is an absolute textbook example of a box fold. The structures are axial planes are going there and there, indicative of small crustal shortening. There's a detachment thrust up here, which cuts off this fold. Here is an example of a chevron fold. If we come down here, this is a classic example of a fault bend fold with chevron limbs on either side, a small box fold there, another thrust, hanging wall anticline, and then a whole series of folds and thrusts here bounded by detachments. Detachment there and a detachment up here. And the whole outcrop shows an overall crustal shortening in the direction of southeast to northwest emplacement in this direction here. Okay, to summarise the first video of this virtual field trip to southwest England, all the information is in the field guide, which you should look at and refer to throughout the whole of these videos. So what I'm going to do now is summarise what we've seen over the last few days. And we started off first by looking at the Ophiolite sequence, the lizard Ophiolite sequence, which is by far the biggest and best preserved ophiolite anywhere in the Veruscan orogeny, which extends all across Central Europe. So what we saw was the mantle sequence rocks here in green at Coverack, and we walked up through the Moho transition zone into the gabbros. The mantle sequence composed entirely of ultramafic rocks, hartsbergites, lertzelites and dunites, composed of olivines and pyroxenes. As soon as you cross the Moho transition zone, plagioclase starts coming in the base of the crust. The base of the crust is marked by the cumulate sequence, which are interbanded hartsbergites, dunites, and interbanded with gabbroic material, cross-cut by troctolite dikes. The base of the oceanic crust is composed of the gabbros that we saw at the north end of Coverack Beach, and these lead up towards the sheeted dike complex, which is at the top of the lizard ophiolite. The pillow lavas in the lizard are not exposed, they've been eroded off, but they would have been above the sheeted dike complex. So above the lizard thrust, the mantle, the Moho transition zone and the crust is all comprising the lizard ophiolite sequence. The lizard ophiolite has been thrust over the metamorphic Searle, which we've seen in Kynance Cove where we are now, at Mullion, and at various places along the west coast of the lizard. These are composed of amphibolites, which are composed of hornblende, plagioclase, with a little bit of secondary epidate. In some metamorphic soils you get garnet and clinopyroxene at the top, and these are granulite facies rocks, but in the lizard these are upper amphibolite facies with just the beginnings of partial melting that we saw over at Cadgwith, Kiltdown Point. In situ partial melting of amphibolite indicates temperatures above 900 degrees centigrade. The metamorphic Searle has an inverted pressure temperature gradient, so as you go structurally down section from the base of the ophiolite, you're going through lower pressures and temperatures through epidate amphibolites to greenschist facies rocks. And the metamorphic Searle is thrust over a series of thrust sheets of sedimentary rocks in the Gram-Scatho group. These are the Devonian marine sediments that lay within the Rheac Ocean between the ophiolite and the continental margin. And that's these rocks here in blue. So the main structural units from top to bottom, the lizard ophiolite, crust, mantle, emplaced over the metamorphic Searle, emplaced over a series of thrust sheets of melanges and deep sea sediments, dominantly turbiditic rocks, deep sea sedimentary rocks, deposited within the Rheac Ocean. Okay, so that sequence of ophiolite rocks is in this area here. This is a reconstruction of the continental margin of South Cornwall prior to the emplacement of the ophiolite. So the ophiolite sequence here, thrust over the metamorphic Searle. Remember, the pressures in the metamorphic Searle are 5 to 8 kilobars, indicating depth greater than the thickness preserved of the ophiolite. So it implies that mid-ocean ridge basalt was subducted down to these 40 kilometers, 40 kilometers depth, metamorphosed, accreted to the base of the ophiolite, and then all of the ophiolite plus Searle was thrust towards the northwest. Beneath the ophiolite and the metamorphic Searle is a whole series of thrust sheets within the sedimentary rocks. These are the allochthonous sedimentary rocks of the Gram-Scatho group, which were deposited along the continental margin of Avalonia, between the continent and the lizard ophiolite, out in the Rheac Ocean. And thrust propagate from outboard to inboard in sequence with time. So you're putting lizard ophiolite over metamorphic Searle, over all the Gram-Scatho group, And all of those are placed onto the thinned passive margin of the Avalonian continent here. Now, when you reconstruct South Cornwall during the lizard ophiolite times in the Devonian, it's actually remarkably similar to the Oman ophiolite, which is by far the biggest and best ophiolite complex preserved. This is a 95 million year ophiolite placed in Arabia, and the ophiolite sequence here is very comparable to the lizard, has all the same units. The metamorphic sole is much better preserved in Oman because we have granulites at the top, inverted metamorphism going down to amphibolites, green schists, and then the entire Hawasana complex is equivalent to the Gram Scatho beds that we saw recently. And all of these were placed onto a passive continental margin in a manner very, very similar to what's going on here in South Cornwall. So the Variscan orogeny, the first thing to happen in the orogeny is the ophiolite formation and abduction onto the continental margin. That all happened during the middle and late Devonian. And then in the Carboniferous, this all locked up and sedimentation continued in the Culm Basin up in North Devon. And that is entirely Carboniferous. It's not related to the ophiolite emplacement at all. And the final stages of the Variscan orogeny were the granites, the Permian granites that are intruded along the Cornubian batholith, and that is going to be the subject of the second video, which will come up next.